Thanks everyone for coming to Bay Area Scala. Thank you to our speaker, Maciej, for doing this three-part course on functional programming in Scala. Over to you, Maciej. Take it away. And I am
Hello,
recording.
everyone. I hope you have your morning coffee. Let me just share my screen and please let me know if it works actually. Sure. Yeah. And here you should now see the slide, which is one of the only two slides I will have today. So do you see it? Like code examples, functions of data, Scala collections, and so on. Yes, thank you.
Yes.
2 weeks ago we talked about all those like more basic concepts. I jumped from one to the other. I think it was a bit too chaotic for an online course because if I can do it seeing you all, then there's always a possibility to just stop me and say, okay, this is too easy, or just ask questions if something is not clear. And right now, like this, it's a bit more complicated. I Today we will hopefully be more focused. I want to talk to you about recursion, some alternatives about instead of recursion, what we can use. We will go through trampolines and lazy lists, and I hope I will have time to talk a bit lazy collections in general. And then about algebraic data types, which is like a very wise name for something quite simple, which is in Scala 2 implemented with field traits and type hierarchies. And in Scala 3, we simply have enums. But okay, let's start with recursion. IntelliJ. And now you should see my IntelliJ, the first file. And yeah, and okay, every time after some example, I will stop and see if you have any questions. If you have, please write them down in the chat. If I just start to go too fast, Salar, please stop me and say that there is a question in the chat.
Will
All
do.
right. The first thing, like the most basic thing that we can write as a recursive function is a factorial. So it means that we have something like factorial of 5 would be as factorial of 4 times 5, right? And factorial 4 is 3, factorial 3, and so on. So this is 1 times 2 times 3 times 4 times 5 in the end. And with a standard way of doing it, it's simply like I have this big int here because it can be the result can be much bigger than int. So that would be simply if n is yes, less or equal 1, then the result of the factorial is 1. Else, if this is n is bigger than 1, then we just do it by multiplying n by factorial of n minus 1. As you can see, IntelliJ shows me already that it is a recursive function. It also shows me where this recursion goes. And if I now do something like this, valres equals factorial of 5 and print, then yeah, it shows me shows me the result. And if I debug it, oh, sorry, I should have put the breakpoint here first. Okay. Oh no, it worked. Okay, so now we have here in the debugger window that we have n, this n equals 5. And if I now go in, so in is going to this factorial, then we have again, oh, too much. We went too far. N equals 4, n equals 3, n equals 2, and when we are n equals 1, then we will go actually to this part, and then we will unwind and go back, and the result is 120. That works well for small numbers, of course. Only when I try to do something like 43, let's say, factorial 43 will be really something big, and big enough that maybe even, oh yeah, like this. At some point, the fact that we just we have recursive calls and so on, means that we get Stack Overflow error. So this is one problem with recursion, that at some point, if there are too many recursive calls, then this will just blow up with a Stack Overflow. The other problem, which we will talk about with Fibonacci, is that it can be slow sometimes. Both of those problems can be, at some point, can be remedied in English, can be fixed with that feature of Scala compiler that lets us write recursive functions as tail recursive. Tail recursive means that this part, this factorial, can be unwinded by the compiler into a simple simple loop, like for loop. The problem is, and that's why it's called tail recursive functions, that this recursive call needs to be the last call in a given function. So we should be able either to return something or to put that as the last thing that happens in the function. And here it doesn't, right? We first call factorial, whatever happens inside returns some value, and then again we have multiplying here. So this operation is really the last one, not the factorial. So to be able to use tail factor, I wouldn't say tail factoriality, but like to change factorial to tail factorial and be able to use that feature that lets us lets the compiler rewrite the recursive calls into simple loops that don't suffer from Stack Overflow. We need to change the implementation. So we can do it, and often it's in fact in all more complicated recursive functions, it is done in the way that we create a nested or just private, but nested works well and is more like easy to understand, like a nested function. Well, let's call it Go here. By the way, I'm using AI Assistant all the time. It helps me. Just as I said before, it's basically lets me copy paste from my own material here, so I don't make any errors while writing code. So this is a nested Go function that looks like this. It takes this number, whatever, the same as here. And so let's say 5 for now at the beginning. And it takes an accumulator, and the accumulator at first will be 0. I can even write it here. And if, no, it shouldn't be 0, it should be 1, because we have this if here. So if n is actually, just like here, less or equal to 1, then we just return the accumulator. And if not, then we call the go function. So the call is the last in the implementation of the go function. We call it with n minus 1. And then as the accumulator to that new call to go is that multiplying of n times the current accumulator. So we're like switching the order of operations here. Here, first we called factorial, and then we multiplied the result of factorial. Here we perform that multiplication, and the result of multiplication goes to the call to go. So we can, in the moment, we will see it in the debugger how it actually works. But this is only the nested functions. So first we also need to write it like this, n. And the accumulator here already has the default value, so this should work well. I can now change this call to factorial to call to tail factorial. What do you mean? Access can be private, of course. Access can be private. And let's just run it. Okay, this is a very long number, but you can see it just showed in an instant. It's not only the thing that it helped us with Stack Overflow, it also helped us compute that factorial very, very fast. So what's happening actually is, okay, this is for, maybe let's change to 5. So it will be easier to see what's happening also when we go down with this counter to 1. Let's click debug. Okay, we are here. And let's say we also have a breakpoint in this place. And we go in. And yeah. So for n equals 5, we are not going to do this at this place. We are not going to return the accumulator, but instead we go here and we will call go again, but see what's happening to the accumulator. It was 1, now it's 5, now it's 4 times 5, so that's 20, now that's... So we take advantage of the fact that the multiplication can be done both ways, right? Before we were doing it like 1 times 2 times 3. Now we are going the other way. We first have n equals 5, then we have n equals 4. We then multiply it by 3, blah, blah, blah. So the result is exactly the same whichever way we perform the multiplication. And then we return the result of the whole go function here, and we have the result, which for factorial of 5 is 120 again. And if, for example, because you can see we have this annotation here. The annotation tailrec in Scala, I need to import it before I use it. And annotation tailrec means that it doesn't say anything to the compiler. It actually says something to me. It's like a tag for me that this method, this function, is supposed to be tail recursive. So if I go and try to rewrite it, try to add something to it, I need to be careful and still keep it tail recursive. There are some complex situations when the compiler is not able to rewrite such a method of a function as a loop. But we don't know exactly. Basically, we shouldn't even care about it that much, unless that makes some performance problems for us. And then it's like on our side that we should try to rewrite it as a loop. If it doesn't, if it still works, then this tells me that, okay, that method should be tail recursive. If I, for example, write something like this, then IntelliJ already knows that because of that annotation, that, hey man, you did something wrong. Either you remove that annotation or change something, refactor that function, because it's not tail recursive anymore. So yeah, I can do it like this, but then but that's not really what I want here. I want here to still have that tail recursive. So I can do it like that. That's basically a problem with tail recursive functions, that sometimes we can see how we can do them. Like usually it is done by adding this accumulator, and we perform some operation on the accumulator, and we pass it to the next recursive call, and then do another operation, and so on and so on. And at the end, we return the accumulator, but sometimes it's not that simple. Sometimes our recursive function can be complicated enough that the way of rewriting it so that it's still recursive makes the code too complex, and we lose the advantage that recursive calls give us. Like a recursive function main advantage is that it's usually much easier to read and much shorter than its non-recursive version. And if we have to write a very complex recursive function, then that's really no use. Okay, let's. I can now see. Look at the chat. Participants and team chat. No. How do I? What do I find the chat window?
It should did you have that zoom
Oh
bar on
yes.
your yeah. Yeah.
Oh yeah, I
There
see
isn't
it.
anything
Okay.
there isn't anything in there right now, just so you
Nothing
know.
about it. Okay.
Yeah, nothing on Twitch
Okay, so
either.
let's go back here then. So yeah, the other example I have here is a Fibonacci function. Fibonacci is this sequence that we have. First, we start with 1 and 1, and every next number in the sequence is the sum of two previous numbers. So for 1 and 1, it's 2. Then we take those two, so that's 3. Then we take those two, well, that's 5, and 8, and so on and so on. And the Fibonacci, the standard way of uh, writing the Fibonacci recursive version is that if n equals 1, then we return, oh, that's E here. If I equals 1, then we return 1, else if 2, then we also, because this I here is the index. So this is the first index, this is the second index. And for two first indices, we return 1. For every index that is bigger than 2, we return Fibonacci I minus 2 plus Fibonacci I minus 1. So that will give us, let's switch. For 5, for example, that will give us 5, because this is 1, 2, 3, 4, 5. For 6, it should be 8, and so on. That's all right. But if I, for example, do 40, that's already a big number. And the problem is not only that it's kind of big, but it's smaller than in the case of factorial, but the computation of it is quite long. If I now change to 41, that's already, we compute the 40 and then add something to it. So you can already see that it's slowly, I have to wait for it for a second or two. That's for 42, that's already, I don't know, 5 seconds and so on. If I change this number to even 50, that's longer than we have time today. So it would be nice to rewrite it as a Taylor recursive function. The problem is that it would be much more complicated. We would have, because to write the recursive version of Fibonacci, we call the Fibonacci twice recursively. So no matter how I do it, like I can't every time if I keep it like this, there's always one of those calls that is not in the tail position. There is a way to do it. I actually maybe even AI assistant can help me with this tail Fibonacci. Yes. And now how do I type a prompt, or I think that this might be a bit too complicated for Derek. Let's just Yeah, keep it like this. Def go, just like before. And we have, yeah, current n, current sum, previous sum, and now if current n, yeah, assistant helping me. Not entirely sure if it helps me the right way. But yeah, but you can see this is not really so easy. And even if I now try to explain to you how exactly it works, that would take a bit. So we have like two accumulators. We add we change their order. We add the one to the other, and so on. It should work probably. Let's try it out. Play out Fibonacci instead of Fibonacci. So yeah, it works. It's the same number. It works much faster. But yeah, you can see that it's kind of getting more complicated. What we can do instead is use one of two alternatives. One is trampolines. Like if we go, trampoline is a way to, how to say it? If we have, for example, call to go, and that call to go, and that call to go, then create another call to go, like this nested one, and this one another, and so on. Then a trampoline is a way to somehow postpone this call so that instead we created like a linked list of calls that are not nested, but after every call to go, one more call, that recursive call, is added at the end of the list, and then we go to the next element of the list. This one is already done, so we call this one. This one adds another element to the end of the list. We finish with performing this one, and so on and so on. So there will be no Stack Overflow because instead of nesting and going like making the stack bigger and bigger, we have like our own stack in a way, which is this linked list of calls to functions. So that helps with that. The problem is it's still slow. So let's write it, but let's not have big expectations. Trampoline Fibonacci will look like this, but we have, first of all, I need to import tail. Exactly, thank you. It's always good to be nice to your artificial intelligence. And and now, okay, def go. Yeah, that's probably right. So what I'm doing here, just only write go I here, go n. Okay, so this is so I won't mistake n and I. Instead, inside the go method, we for this index, I don't just return the result, but I return the tail rec of that result. Tail rec is that like well, the list that inside the result inside that list. And for the index, if this is 1, then I'm saying, okay, finish. This is already the end of the linked list of calls. Sorry. And I return 1. For 2, the same. Otherwise, we're doing this. We call tail call. So like we add something to the linked list, and that tail call is the call to this method for I minus 1. And then we're doing tail call for once more for I minus 2. We get these two results and we yield. So like our new result is A plus 2. And here, because go of n returns tail rec, we need to extract the result. So this is cool. duplicated because I already wrote it somewhere else. But if you go to tail call here, you can see how it's implemented. That this part here, column and then the arrow, tells us that this is a lazy computation. We will also meet it again for lazy collections. It means that the call to this go here is not performed immediately. So it's not like I perform the call to the method go and then get the result, and then that the result is a parameter to tail call, but actually the whole operation of calling the go function is the parameter that goes inside the tail call, and only when we come to that point in the linked list where it should be called, then the tail rec that structure performs the call, gets the result, and performs the call to the again, and then gets the sum of it. So if I now trampoline Fibonacci of 42, that will be long. Let's do it just for 10. And if I also, let's say, put the breakpoint here and debug. Yeah, so for 10, this will now add the call for 9. This will add the call for 8. Yeah, now the working with the debugger is a bit confusing because I'm not in charge of when that call to go will happen. So I'm just I can only see here in the debugger for what I is this call made, but it's not done exactly in the same order as I would like it. Yeah, as I would
Sometimes
imagine.
if you break that on multiple lines, then you might be able to separate the calls for when it's queuing up that operation versus when it's actually.
So, okay, because this is like we are also using the foiled syntax here, which enables us to see better, like it's more readable. But what's happening actually is tail call, this go, okay, and that is flat maps for A and tail call of yes, and then we are mapping the result to A and B. Yeah, so, but as you can see, probably foiled notation is just nicer. Okay. Yes, but anyway, this is kind of slow. I might try to, if I run it for 40, it will take some time. I think I was able to get the result eventually, but it's a bit, oh yeah, now it's done. And you can also see, like, if you look at both, even all three versions of Fibonacci, you can see that this is not really well optimized because, for example, for the number 5, if I want the result for Fibonacci with I equals 5, then I call Fibonacci for 3 here, and I call Fibonacci for 4 here. But then Fibonacci for 4 calls again Fibonacci for 2 and for 3, even though I already did call Fibonacci for 3. So certain operations, practically a half of them, is performed twice, and if the number goes up, then the more calls go, the more those nested calls are calls to the for parameter that probably is already somewhere there computed. So it shouldn't be necessary to call it so many times, and so. And that's not solved by trampolines. Trampolines can only solve the Stack Overflow, but not the performance problems. It is solved by compiler in the tailreg versions, but as you can see, this is already getting a bit unreadable here. What we can do, one more version of Fibonacci, is use a lazy list. Lazy collections are collections that don't have, like if you, let's write it like this. If I have a normal array that is 1, 2, okay, let's use the Fibonacci here, 2, 5, 3, 5, 8, and so on. So that's like a normal array of already known numbers. We can say that this is exactly like if I have 1 and 1, and here we can say that, okay, we know what will be every next number, but we, instead of number here, we should be able to somehow write the like array of a minus 2 plus array of a minus 1, given that this is array or list. Okay, let's call it list so it will be easier though. So awesome. One thing that you can see that in fact this makes that list infinite, right? There is no, if I, for example, ask for a number of 1 million, then the list will just happily try to get that number by first computing the number for the index 3, then for index 4, and so on for the million. But the good thing is that for every time I already have a number, so this will be 2 here, then it will be 5, then it will be 5, 8, and so on. That number is already computed. So after I computed once, this is already put in the list, and when it will be needed again here, it won't be computed once more. It will be just I will just know what it is, so I will take it from here. So yeah, in Scala we can do it with such as a bit strange notation. We can private val. Let's call it fib, and fib will be big int of 1. And there is this operator that connects, like creates a lazy list from the elements. So first we have a lazy list that has this element and this element, and then we add one more element to the end of the lazy list that is exactly this part, like the code that will give us every next element. What it does is that we take the fib, our lazy list, we zip it with fib.tail, where fib.tail is everything except the first element. So it will be like for 1, it will turn this list into 1, 1. Then for this second element, it will turn into 1, 2, and 2, 3, and so on. So zipping with its own tail creates a list of tuples that are like consecutive elements of the original fib list, and then we map that every tuple to its sum. So, and that's our next element. Okay, and when we have it, this is just our like this lazy list is our not yet realized, not yet like a data structure that for now it only exists in the form of the 2 first elements, and then some code that will produce the other elements. And what we do here now is just fib, take n, and call the last of them. So take is like for every collection in Scala, we can use the method take to take the nth element of that method. For lazy lists, this is overloaded in a way that if I take the millionth element, which does not exist yet, the lazy list will use this code here to actually go from those two first elements to and produce all the elements that is all those intermediary elements that are needed to eventually compute the nth, the millionth one, and then from all those it will give me the last one, so the millionth one. Sorry. Okay, and so now I can do Fibonacci lazy list of 40. Let's run it. Yeah, it's very fast now. I can do even much more than that. And that is also very fast. So I think so maybe let's do it like that. Recursion is usually a bit avoided in real applications because it can easily get complicated, and sometimes you can think, okay, why do I even do it if I can write the loop itself? Especially, okay, maybe you can do the tail recursion, but then if your recursive function becomes more and more complicated, then writing the tail recursive version of the same function becomes so complicated that it stops being realistic. Then you can use trampolines, but that doesn't really solve that many problems. Only it helps you, like guards you from Stack Overflow, but it may be the result may be slow, like the computation may be slow, and sometimes it really looks like the same version of the original version of recursion, which sometimes helps, sometimes does not. What I would like to do, like you to maybe remember from this, is that lazy collections in Scala, especially in Haskell, in maybe also in other languages, is a quite nice alternative to recursion. A lazy list is like a more powerful one, but you can also use a simple iterator or a view, and those are like a simpler versions that help with help you with writing code that is only doing as many operations, as many computations as are needed, while it still looks pretty much readable and concise. For example, I'd like to only here collection view here.
Actually, before you leave this one, I've got a question
Yes.
on that fib variable. I'm a little confused. I don't remember how. So you get a variable, but the initialization expression contains a reference to the variable. I'm a little rusty on how
Yes.
that. Yeah, I understand a recursive method, but this is sort of a recursive val variable. So I'm a little confused on how that's allowed.
Yeah. Yeah, this is in Scala. This is allowed because what we do here, if we only declare that fib, it's lazy. It means that that this part is not called yet. Like what you see here is similar. Let's see what happens if I just go here to implementation of this operator. Yeah, you can again see this notation, colon and arrow, and that means that colon and arrow means that if I have, for example, def foo that takes a number, but it takes that number in this lazy way, then if I call foo, I like 1 plus 2, or maybe something like this. Okay, print line hello, and then 1. So what's happening here is that I don't call this println hello and then return one, and that one goes here, and then that one is incremented. What happens is this whole part, the whole expression here, is actually given to foo, and it's only computed at this point.
Yeah,
So
yeah,
what's
I
happened?
understand. Yeah, that part I understand. Yeah, I understand the pass by name, but it's the fact that on line I can't read the numbers. The declaration line were private val fib. So I'm a little confused. So after the equal sign, there's some expression. So even if part of
Yeah.
it's going to be deferred, just to make the deferred thing, you've got a reference to the variable, except that that's the expression that's used to initialize the variable. So
Yes, yes,
I don't quite
exactly.
remember
So
how Scala allows that.
yeah, that's just Scala compiler. I take advantage of it. I don't really know what this compiler doing, but anyway, the compiler has all this code already, so I guess so this is allowed from the compiler point of view. That this part is not yet evaluated, and Scala simply says, all right, we can create a lazy list that is using its own itself to create new elements of itself. Sorry, I don't know how the compiler is implemented here.
Yeah. No, I'll dig into that.
All right. Yeah, I can also I would also like to show you this how lazy collection works on some other examples. For example, we have here just numbers from 1 to 100. And what we do here is like a simple operation when we map every number, we square it, and then we filter for this number if it's bigger than 100 and it's even, and then we take first such element. So that seems pretty easy. We just like if it's written like this, then what's going to happen is that we will first square every number from 1 to 100. Then we will perform filter on the whole new sequence that is those numbers squared. And only when we have all of them, we will take the first of them. And so quite a lot of unnecessary computations here. We can, of course, help ourselves simply by using find and then calling a get. So this find will stop at the first number that fulfills this requirement. So that's better than using filter and then getting head. But imagine what's happening if I want 2 instead of just 1, right? Not only the first, but I would like to take 2. So there is no such, yeah, I would need to make it into sequence of ints. But there is find for finding the first, but there is no special method for taking 2. So I have no other option if I don't use some smart data structures. I have no other options than using map and filter and take 2. What I can do actually is use view, which is a lazy collection. And what's happening is that a view is basically not performing operations that come. It overloads those map and it overloads the filter, and it doesn't overload head because it doesn't. This is exactly the moment where actual operations happen. But map in view is just giving this parameter by name. So instead of just mapping n into n times n, what it does is maps n into a piece of code, like a lambda function, that when that lambda function is called, it will perform the operation n times n. Similar for filter, instead of just performing this, I will only give a piece of code that when called, it will give me the answer. So what's happening instead of making a new sequence here that is full of squared numbers and then filtering that sequence for only those numbers that are bigger than 100 and even, we can say that it happens the other way around. I create a view, I map my number to a piece of code, so that lambda function. Then similarly, I will filter those. But what I want, but only here when I call head, or if I call take two, that only tells me that what I want is those two first elements that fulfill certain requirements. And what are those requirements? Well, those requirements are that they are bigger than 100 and 0, and that n here, which should be bigger than 100 and even, is actually a result of this piece of code. So let's call this piece of code for the first element in the original sequence of numbers for 1. So 1 times 1 is 1, so it doesn't fulfill the requirement. And I go through the numbers 1, 2, 3, 4, and so on. And at some point, the number 11 is 11 times 11 is 121, so it fulfills this part, but not this part. 12 times 12 is 144, so this is my first number. And if this is head, then, this is the first number that fulfills that I'm taking. And then I'm looking for the next one, that will be probably 14. And that's where the whole computation ends. So the numbers between 15 and 100 are not taken into account completely, like they are, because I already have everything I need here, then I don't need to perform any computations on 85% of my whole sequence. So yeah, at some point in a different lecture, I said that usually we look at performance of programming languages and other technologies in the way that if the programming language is more close to the metal, like C or C++, if it doesn't have garbage collection and it doesn't have abstractions, then we usually think that it's faster. And if I have unlimited amount of time of working with the code, then probably I can make it faster, that's true. But if in the real world, we have deadlines, and that means that often we only can write simpler versions of some basic version of some algorithm. So, and only then, if I have a bit of time, I can work on some optimizations. And in case of language like C++, I will probably just write the basic, like the basic version of some algorithm, and optimizing it will turn out to be quite complicated. While in Scala, just by writing this part, those 5 characters here, I'm already getting a much more performant version of the same code, of course, only in certain situations. But anyway, like in languages on higher level, like Scala instead of C, we have this ability to perform certain optimizations much faster. And that gives us a leverage. Like we can, because in the real world, we don't really compare algorithms that are exactly the same and one works in Scala and the other works in C or C++. But instead, we can think of it like this, that in C or C++, we will probably have time and energy, and because we also have to debug it, we have to test it. We only will have enough resources to write certain simpler version of an algorithm, while in languages like Scala, we will have time and capabilities to write something much more complicated, much more performant, like optimized, and that's why we can still be on the same level, or maybe even faster sometimes. Yeah. Other questions? Yeah, there's also iterator, but I prefer view because iterator is a bit unsafe when you it goes through the elements of the sequence one by one, and then it ends, so you can't use it twice in certain situations. So view is more is every time you use view, it's always from scratch, so to say. All right. The next thing I wanted to show you is actually quite a bit more complicated. Right. Now not this one. This one. Let me just look. Okay. Algebraic data types is a name for a concept that we can have. Maybe I will help myself and just look at Wikipedia. Yeah, so we can have like a data type that is formed by combining other types. And because we always because we can have like a finite number of those basic blocks of elements, that means that we can kind of know that there are only a finite way to deal with those elements. And if we can prove that we already dealt with all of them, that means that our code is safe in a way, that there is no way to perform certain logic in a way that is not handled, that we don't have such cases. So what in Scala 2, we didn't have enums, so algebraic data types were done with traits. We have a field trait of something. Now here we have a tree, and that field trait of something had, for example, case class of branch, and let's say we have also case class of leaf and case object. And because it's sealed, the sealed keyword tells us that all subclasses, subtypes of that tree needs to be in the same file. That means that if we already have those case classes and case object, then we can say that, okay, if I want to perform some operation on a tree, then what I need to handle is this branch, is this leaf, and this stump, and that's it. No more cases that I should handle. Like if I have code that takes care of those three options, then that's it. The problem was that this is kind of wordy. As you can see, if we have a branch, the branch have left tree, some value, some right tree, then I have to write that it actually extends the tree, and leaf, so like the end of the tree, like this one is also needs to extend the tree, and stump, which is like this point in the tree that there is nothing there, also need to extend the tree. In Scala 3, we finally got enums. It's kind of I don't know why it wasn't introduced before, I did a little bit of research, and what I got is that basically there was an idea somewhere around Scala 2 point early number that the features of Scala are flexible enough that everyone can write their own enums if they wanted. And actually, yes, there was an enumeration library, and there were some other attempts to create enum by as a third separate library. But it never worked right. So people quite quickly started to write this code that looked a bit unreadable with traits and case classes. In Scala 3, that was finally fixed with the new keyword enum. And now, if let's write it maybe from scratch. We have, for example, enum 3, just 3. And that will be an enum that has that has a branch left, and here the value is int, so that number here. Then we have leaf, which is the end, also a value, and the stamp, that is this nothing here. And because we have these are the cases of an enum, then that's it. We already know that branch is a case of 3, and leaf and stamp. But if you want to make it a bit more generic, so just use a generic type T here and a generic type T here, then I need to add the generic type to the tree. And also everywhere else, we need to have tree of T now. And that doesn't work yet, as you can see in the case of stamp, because stamp doesn't have a value. And but it cannot. Scala compiler, well, of IntelliJ, cannot determine this type argument. We don't have anything here. This is done by adding plus to the generic type. Plus here indicates that this tree is a tree of anything that is of the given type and all its subtypes. That fixes the problem with stamp, but it might not be intuitive how does it actually happen. And to better understand it, we need to also know how it works with traits, which enum is on the Scala compiler takes that enum and it turns it into bytecode that is basically the same as in the case of traits. In traits, if I now write the same thing once again, but with 3 like this, and case class, yes, exactly. So okay, this is what I wrote before. In case of enum, but for where value is an integer, so we have a case class that extends a tree, and case class leaf again that extends a tree, and case object stamp that extends a tree. This is a case object because in terms of the instances, there's always only one stamp. Because there are no values inside the stamp, then every stamp, if no matter where it is, really is equal to every other stamp. So we only can say that there's always only one instance, and that means if I write now T here and change this, and now I add this everywhere. And now I also need to add this here and here. So we have this problem with stamp because we don't have a value. So every branch and leaf can be parameterized with the type of its values, but there's only one instance of stamp. and we need to add some kind of a type for tree, and that type in Scala will be nothing, because like if we go from t, like let it be int, and then we have some kind of a like a subtype of int that can be whatever. There's always like an artificial type added by the Scala compiler that is called nothing, and that nothing type has no value and is the type that is a subtype of every other type. Like whatever you have here, you can have a string, your own case class type that you just wrote. Everything that you deals with in Scala, it has at least this one subtype, which is called nothing. So, and now, because we have a stamp extends a tree of nothing, for it to work, we need to say that our field trait of t can be any type, but also it needs to be possible to give it any subtype of that, whatever we choose t to be, and that will be at least this nothing in the case of stamp. So in the case of enum, it's a bit less visible, but that nothing is still here. Like this, the part where we extend the branch is not needed because we already know that branch is a case of tree. But here we would still have this tree of nothing if we wanted to write it explicitly, but we don't. All right. Yeah, so what I wanted to do, because we already talked about recursion, and before we talked a bit about pattern matching in Scala, so I want us to do now is to write a tree of integers. So, okay, but using that notation that it can be a tree of whatever else, whatever we want. And I want to print it out in maybe not in this very nice form, because that would take too much time. But let's say if we have this tree that is, so we have this first root element that has a value of 3 and has a left branch and a right branch, and the left branch has also like a value 2 and a left branch, which is a leaf, so the end element with 1, and on the right it has nothing, so a stump. And on the right, it has 2 leaves. That branch with the has element a value of 5 and 2 leaves 4 and 6. So what I would like to see is that we have 3, which is then on the left it has 2, which on the left it has 1, and then we go back and to the other side, and now we have 5, and this has 4 on the right and 6, that's 4 on the left, 6 on the right. So something like this. This will be completely sufficient. Let's leave it here just to see how it works. And so yeah, let's just shrink. Yeah, and the shrink. So we don't need this. So n of n. Yes, okay. So let's say just for the just at the beginning, the simplest way we can do it is just print line the tree as it is, nothing else. And int tree will be this tree, so just tree in the tree. And this I can remove, this I can remove as well. Okay, and Let's see if it works. Main is already here. So I can comment it out. And let's go again to enums. Let's try again. Okay, so what I got, because I'm using the enum here, so already this printed out version of the tree doesn't look so bad. It's just what I wrote here in the form of a simple string. But I would like to make it into something like this. What I can do is to mix the fact that I have the complete list of all the cases. So a tree can be a branch, a leaf, and a stump, and I can mix it with Scala pattern matching. So what I can do this is that I can take the int tree, which is an enum of the tree, which can be one of those 3 branches. I can do match, and already I can use a feature of IntelliJ IDEA that lets me make an exhaustive match, because I know all the 3 possibilities, so I can already, IntelliJ can already write them down for me. So it looks like this. I have a branch, a leaf, and a stump, and for depending on if this int tree is one of those 3, I can do different things. For now, let's say what we actually want, we will just we won't write anything here. Print line actually, print line of just empty string, and here print line of empty string. And in case of stump, we will write X. This is actually the code. The other 2 are just like a placeholder for something more complicated. But what still needs to be done is this number of minuses here that will. I wrote it in a bit, not here, but here. Sorry. Yeah. So what I want to do here is also to have some this number of minuses in the right number. If I go to the stump that is somewhere nested here in the tree, I want to know on what level it is. So the level is exactly so like prefix. Yes, already. So this is a way to have a sequence of minuses. This number of minuses is so many as this level variable, and then I create a string out of them. So, and this will be then prefix and X. Yeah, and now if I can remove this part, but if I just run it now, and nothing will come up, because int tree is not a stump. What I would need to do is to just, instead of int tree, just write down here a stump. And why nothing happened? Let's try to debug it. Of course, because I used the int tree variable. What I should use is the tree variable. And now, so yeah, I have X, but that's not really much. I can also like 3 here as like an artificial level, and that will give me 3 X's and then there. But I want to start from the start. All right, so let's do the same, but for leaf. If I have a value, so this is no longer this case, but this case, I just have a leaf as a value. Then what I want to do is to, again, have the prefix and then the value. That should be easy enough. If I now write leaf of 4, and run. That gives me 4. Actually, I don't really need this toString here. And the real problem is how to do with this tree branch, which has a left value and right. What we can do is print left level +1, then print line the value, and then print again right level +1. And that should give us already the whole thing. Yes, but not exactly what's happening. Yeah, because so yeah, this is what we may want actually, because what's happening here is we have to choose the way we traverse the tree. What's happening now is that we have the sprint here that goes to the left, and so we are going from 3 to 2, then we are going from 2 to 1, then we print 1, then we go 1 level up, and then print 2, and then we go 1 level up, we print 3, and so on. So this gives us actually the version of the printed out tree that first is 1, 2, stamp of the 2, then 3, then 4, and this also, like, we have 5 here, 4, 6. If I just change the this thing, if I move it here and run it again, then we will have something more similar to what I wrote here. 3, 2, 1. Only that levels should start with 1. Great. Yeah. So what's happening is that we are able to traverse the whole binary tree with only this quite simple piece of code, and we can print out all the cases. If you also recall from the first lecture, almost the same notation with cases is used for parse-hole methods. So generally in Scala we can see that we can match something against some cases in this way, but we can also write a method that takes only 1 or 2 cases of a given data structure and only performs some operation on it. And the code looks very similar, and it's also readable. All right, since we have a bit of time more, I would like to make a more complicated version of this code. Let's say, okay, this int tree looks like this, but that's because I already wrote it from scratch. But what if I would like to first, like, let's say, write something like this. We have, I would like to have a method that adds a new number somewhere inside. For example, if a binary tree that looks like that, because if I add like let's say 7 to this, then I look at this and I see that 7 is bigger than 3, then I go to this part and again look here and I see that 7 is bigger than 5, so I go right. Like for bigger number I go right, for lesser number I go left. And then here, what I want in this case is to add one more branch, one more element, and add 7 here. And then if I come again and let's say add 10, then that should go again here. But if I add 8, that should go somewhere here, and so on. So if I, for example, want to do that for -2 should end up here, and -1. And then if I add a -1, that should go even more here on the left of -2. So it depends on also not only on the value, but also on the order of adding. We already know how it works for ints, but our tree is a tree of whatever. So we need to create a compare method that will take 2 elements and compare them, and then gives us information if we should go left or right. And then what we want is, like, we get the tree that we have now, we get the new value, we have that compare method, and what we want is a tree that has this one new value added somewhere there. So what we do is we can again match exhaustive for everything, and let's say that let's write that new tree that adds 7 to the int tree. So again, just like before, we need to think about each of 3 cases here and perform some operation depending on where we are. First of all, let's start from the simplest one. If we have a stump, so let's say this 7 eventually leads us to here, right? To 5. Let's just remove this. So 7 is bigger than 3, 7 is bigger than 5, 7 is bigger than 6. At some point, we will try to go to the right of 6, and that will be a stump. And what we want to do is to, instead of a stump, create a leaf of the number. So what will happen is, if, for example, we only have 0 elements because we have only a stump, then that 0 element will change into just a leaf with 1 element with the new value we add. We can actually go do it one by one. Let's do it. Print, it's all right, but let's do it like this. Our new tree will be just a stump. And yeah, 3 of nothing, that's all right. And our even newer tree, new tree of 2, will be add new tree. Yes. And add 7. And then we want to print new tree of 2. Yeah, that's exactly what happened, because we started with the tree that is stump, and yeah, we start with a tree that is a stump, so we don't even need that compare method yet. We just go through the cases, and okay, the tree is a stump, so we just replace it with a leaf with this value. And then we go to the print method, and the print method uses this new tree that is now just a leaf, and we have a level of 1, so just 1 minus, and then the value of 7. And now, if I want to add 1 more, so new tree of 3, and that will be add to the new tree of 2, another value, let's say 2, and yeah, the same compare method, we can actually take this compare method and just make it into a private def. Yeah, compare. So we can just give it here. Then we need to now implement the leaf case, because if I just call it, if I run it now as it is, it will tell me that implementation for this is missing. Even though before it worked, this was not implemented, but for stump it worked and it didn't need the parts for leaf and branch. Now it needs one. So for leaf, what we want to do is we actually have two versions, right? We have if we have a leaf with a number 7, then we want to go either to the left if the new number is less than 7, or to the right if the number is bigger than 7. So here I need to add a guard if value is, so the other way, if compare of t and value is less than 0. So if it's less than it is, then if we should go left, then what I want this tree to be this leaf to be replaced with is a branch. Leaf turns into a branch where on the left we have a leaf with a new element. That value, that was a value of the leaf, still is the value, but now it's a value of this branch. And on the right, we have a stump, because this is exactly a situation that is here with 2. Imagine that 2 already exists and we want to add 1, but so 2 is a leaf, we add 1, so we change the leaf into a branch, add 1 on the left of that branch, and we create a stamp here, so it indicates that there's nothing on the right to 2. Okay, so we need to do similar thing for case 3 leaf of value if compare of t and value is bigger than 0. And that will go the opposite way. So we have stamp, we have value, we have leaf. Why do you happen to funny? No. Compare. So it should be right. Let's try to run it. Yeah. Okay. So we have first we had let's go this way. First we had a stump, then we add 7 to it, and that 7 was a leaf. Now we add 2 to it, and that 2 goes to the left of 7, and on the right we also create stump. So okay, so now our tree looks like 7. Looks like this. It has only 2 on this part. Let's try to add 10 to it. So now it will have also the other part. Sorry. And now the problem is that we will again get that it's we go the unimplemented path, because the 7 now is a branch, not a leaf, not a stump. So we need to do something also here, and that's the most interesting part, really. So if we have a branch that is left value right, and we know that the new value, compare t value, is less than 0, so it should go to the left, then what we need to do is to see how the left part will change, new left. So we call add recursively for left t compare. So what we do is we call this add on the left sub branch of the place where we are, and we create a new left. Then we replace the actual the branch we are on with new left. Value stays in the same place, right stays in the same place. The only thing that changes is the new left. And similarly, for when it's bigger, then we have new right, and we switch. We do this like this, and then we have left value, new right. Right. This is not necessary. Yeah, so this way we created a tree that has 7 at the top, 2 on the left, and 10 on the right. I can also change this, because now I always create a new instance, a new reference for every step. But let's say we do it like this: sequence 7 to 10, and now I can just map it into some n. No, basically not map, but let me just take a look. Create no fold. So fold left, start with a stump. Fold is that method that we take some initial collection. In this case, it will be a stump, and for every element of the sequence, we transform the initial collection into some other collection. So in this case, we just add and add 3 t compare, so that will be right here. 3n 3 n compare. Yes, 3 of n. Right, fold left 3. And that will be our new tree. I can remove this part now. And that should give me the same result. Yes. But I can just, having this code, I can just now add other elements, and they will be all put in the right places in the tree. And again, we did that only by pattern matching and having all those cases covered, which are not so many of them. In case you, for example, get a number that already exists, we can just also, let's see what's happening if I just add another 10. Will it work? No. So that's because we didn't cover the cases for where the compare returns 0, so where the things are the same. So let's tree branch of left value, right we don't have to write that compare because it's the only what's left. Like we already covered cases where the compare goes is less than 0 and what's bigger than 0. So what we do here is simply we don't even have to create a new branch. We just can return the old branch. So it's done in Scala with this monkey operator. Do I even need to write it? No, probably not. So branch, and same thing for leaf, case leaf of 3, leaf, also leaf. And now, still something wrong. Leaf 10, match error. No. Okay, let's try to see what's happening here. Debug. No, it's something on the compilation level. 3 of leaf value. The leaf value if compare. Okay. What if I just do it like this? Now it works, but what I would like to actually do is not to create a new leaf, but that won't work. No. Okay, so I should also do this here. I can't just leave it. Okay. So yeah, so now we have all the cases covered. So for situations where we have a new value that is less than the actual element and that element is branch, or bigger than actual element and that element is branch, or because that's the only option left, it's exactly the same. And same for leaves, and for stamp, we don't have to check anything and just we turn the stamp into a leaf. And yeah, so that's a binary tree, which can be sometimes in other languages quite a complicated thing to implement. And here we have it simply in this much code. And we also can print it out in a very simple way. Okay. Are there any questions?
I don't see any in Zoom chat or Twitch.
Yeah, because we went through it quite quickly and we still have some time. So if you still have time, I can go back to one thing that I didn't cover 2 weeks ago. It's called early returns. It kinda also work with lazy collections, so it's connected here. Only that we don't. And it actually uses pattern matching. So the thing is that in Java, in Kotlin, we quite often use early return as a way to go to jump out from the from an operation when we already have the result, and we don't need to look for more. So one way to do it, I already talked about it for a moment, is that lazy collection in Scala, that we can, instead of just mapping and filtering and then taking the first element, we can find a way to do it in a more smart way that we only perform those operations until we find that first element. But there are also ways that situations where that might not be the best way, the best solution. And it's also a showcase for me to tell you more about pattern matching in Scala. So here we have like a artificial example, but something that you may find in your work. We have something that we have like a database of users. And those users have some names, have their age. And let's say that we have also in the database a map of user IDs that maps a given user with this ID to its parent. So of course, some of the users will not have its parents, their parents. And for one user here, I introduced an error that Emily Johnson has simply has a parent that is not in the database, even though the parents map says it should be. And another thing is that some of those users have emails that are not valid like this. And let's say in our code, what we want to do is to check if our user is valid. And then if that user is valid, then we first we only have user ID. We want to convert that user ID to a user and then check if the user is valid. And that validation can be either if the email is valid, or a more complex validation would be if it has a parent in the database, and the problem is that sometimes we can have an error and that parent is in the parent's map, but not actually in the database. Anyway, how it can be done in Java, for example, is that we just go through the list of users in this case, of user IDs. Our complex conversion would be to change the user ID into a user. Then we perform a complex validation. And if that works, then we return that first valid user. Otherwise, we go through more users, and at the end of the collection, if there is no valid user, we, for example, return null. And that can be done in Scala in a very similar way. Like let's just have this and this. And first valid user would be something like for user in user ID. Yeah, exactly. So first I perform this complex conversion from user ID to user data, and then I perform some complex validation. That validation returns true or false. If it returns true, then it returns some user data. Otherwise, well, I can return none. Because in Scala, we also don't like to use return, but in this case, we don't like to use null even more. So let's do it like this. Fine, but that's really just Java with some changes. And let's try to do it in a way that doesn't use this nested return here. Instead, what we can do is use the very naive approach. So we have user IDs. And user ID is a sequence. It has the find method, and the find method means that we can take user ID, perform a conversion of user ID to user data, perform a complex validation. That complex validation will give us true or false. And for the first user that complex validation will return true, what find gives us is that user ID. So we again have to do the complex conversion from user ID to user data. So in the end, what we get is something that's not entirely performant, right? We perform complex conversion twice, and it takes a long, long time. It can take a long, long time. So fortunately, well, Okay, let's do it step by step first. Scala has those collect methods and collect first. We talked a bit briefly in 2 weeks ago. So instead of using find and map, we can merge it. Into just collect first. What's happening here is just that we just take the user ID. We perform, this is exactly the same as before, we perform a conversion and validation, and if it works, we perform the conversion again. The only good thing is that now we have it in one as a partial method inside of collect first. But that already may give us an idea. This is a case of this is a partial function, right? It will only return if this part works. So we can write our own custom pattern matching that will check conversion and validation, and it will give us user data instead of user ID. So that is done in Scala with an apply. So an apply is like a opposition of apply, in the sense that if we use apply, we can give it a parameter and it just gives us like a smart constructor. It can perform some logic and give us some data structure. Here it goes the other way. An apply method is one that will give us will take a data structure and will give us elements inside that data structure. So what we get here, really, maybe better, let's first write that collect. Right, okay. So what we have is that for every user ID that we call the collect first method from Scala collections, what happens is we try to get a valid user. And the valid user means that that user ID goes to the unapply method, and we get as the result, we perform that logic, we find the user, we perform the complex validation, and only if that user ID is already so that's a something like complex conversion of user ID. User data and complex, that's user data, yeah, and if, yes, this is what I wanted. So we perform the conversion, we perform the validation, and if validation works, we return user data, otherwise we return none, and in that case, the pattern matching works and we get a user. This might be a bit unintuitive in the way that I can use this unapply here to get a user from user ID, but I could also do something like this. Valid user equals user ID. Only I need now to put it somewhere in the code. Let's say like say here. So if I have user ID that is, I don't know, 5. So what's happening is that for that number, I perform all this logic, and if it works, I'm getting a pattern like a deserialized version, the result of all that logic. But in the place where usually we would think that we will just put the parameter in instead of getting it out. Yeah. And same happens here. For the user ID, I call unapply, I get that user data, validate it, and if it works, then I'm getting out that user here. So that basically covers the situation where we, because we now only have one conversion and one validation, and already if that works, I get user data. So, and if the first time I get that user data, then collect first already returns it as an option. What you may also notice is that this is not really that that easy to write. So, yes, because at the beginning we just had this code, this for loop. Now we have a more code that looks more complex, and that is right. But that code is only complex at the beginning when we use it for very simple things. But at the moment we start to add new, more complex logic to the validation and to the conversion, then it actually turns out that this kind of this logic that works with this by pattern matching is much better fit to accommodate that additional code. For example, if we have, let's say, we need a safe complex conversion. So now this complex conversion here, which actually, let's say this is database, find, yeah. So let's say that complex conversions means that for this given user ID, we go to the database, we find a user with a given ID, and we are sure of it. Like every user ID we give to complex conversion should be in the database. So just use get. If it does not, it blows up. But now we have this safe complex conversion, and what's actually happening here is that we just either find user ID in the database, or if not, then and if we do, then we return a sum of user data. If not, we return none. And now writing this code in the safe imperative way becomes more complex, because what we have here is that for every user ID, we perform a safe complex conversion that gives us an option of user data, and only if that option of user data is actually working, if we have a user data, only then we can perform complex validation, and only if that validation works, then we call return sum of user. You can see that this return here becomes like even more nested than before, and if not, if all that doesn't work, then yeah, we return none. Yes, this should work now. So yeah, and in case of what we wrote here, the same exact code is actually simpler than it was before. So what we do here, unapply, after all, returns an option. So what we need to do is simply perform a safe complex conversion. And if that safe complex conversion works, so that gives us some user data, then we call find on that sum and perform complex validation. So that we can get either none here and it will return none, or we can get some here, but validation doesn't work, and then we again return none. Or it can work here, we get some user data and validation work, so we return some user data. And this here for all user IDs works exactly the same as before. So in fact, instead of this code here that took 2 lines, now our unapply is, well, okay, you can say that it works like this, but it can be also written like this. And actually, our loop, our collect first called on user IDs is the same. But what if, for example, we have one more validation, right? Like it can be that we have some kind of validation, for example, this validation that is looking at the email and say, okay, we only want someone that has a valid email. But let's say we can say that someone is valid even if the email is wrong, but for another reason. For example, maybe it's maybe user data John Doe with wrong email is a child of Michael Brown, and everyone who is a child of Michael Brown is valid. I don't know. Let's say but anyway, we can have a possibility that someone is valid not in our first way, but in another way. In our version of this logic that is using pattern matching and unapply, this can be done like this. We can have, I don't know, some kind. I will not implement it. Simply say that we have like a more than one validation, and we can have, yeah, this is also not needed here. And what we do here is we used exactly the same unapply that was before, only our other validation is something else. Like before it could be the email, now it can be who is the parent. And what do we do to find the user this time? Simply, user IDs, collect first, and we just write one more line. So if user is valid in the usual way, for example, because the email is valid, then we just return it. But let's say the user has a non-valid email, we only then go to the second case and check if that user is valid in a different way. And that's it. That's all we need to add to our logic to be able to validate the user in two ways. All right, and the last thing, as you might notice, this code, save complex conversion find, is repeated in many places. Like we have unapplied this, we have also probably it should be somewhere here, maybe not. Anyway, we can extract our logic that uses complex conversion, like conversion and validation, to an upper level, so we will not have to do it all the time. We can create a trait called, for example, deconstruct, and it will deconstruct our user IDs to a user data. So this will be user ID to user data. And then we will need to provide a conversion method, a validation method, but the unapply will be the same all the time. Unapply will be convert and then find, validate. So what we have here is, let's say, what we need to do is simply write this. So a valid user foo, and user IDs, valid user foo. Why? So what's happening now is I took this piece of code that is repeating every time. I put it in one trait that is working for any two types of data. And now what I need to do is to just provide information that for the given pair, user ID, user data, I use this method as a conversion and this method as validation. And everything else is already taken care of by, so like this part needs to be written only once for the whole code base. This part needs to be written only once for a given pair of data that I'm converting and validating, and this is how I use it. And this is it. Are there any questions?
On in the chat, and I'm just about to look at Twitch just to make sure. No questions in Twitch either today.
Okay. All right. So thank you. Let me just go back to. And yeah, that's all for today. Tomorrow, in 2 weeks, we will talk about monads a bit, and then about system effects, and the example will be how to use cat's effect to perform some operation on the database.
Fantastic. Really enjoyed the live coding and low slides. That was great.
All right. Thank you.
Thank you. No, thank you so much, everyone, for attending. Thank you for Maciej for the presentation, and see everyone in 2 weeks. Have a nice weekend.
Thanks. Bye.
Thanks all. Bye.
Thank
You
you.
too. Have a nice weekend.
Bye.
Bye.